Okay, in this podcast, we're going to talk about how you would determine the pH of a mixture of different acids. Okay, so in order to do this, you absolutely have to consider the strength of your acids. Your strongest acid is really the only thing that needs to be considered here. So, like here, for example, we have HBr and H+. So HBr, strong acid, completely dissociates into H+, Br-. So this completely goes to completion. So whatever the concentration of the original acid is, that's going to be your H+ concentration. Now, a weak acid is an equilibrium. So not all of this is acid, this bound acid is dissociating and giving us the H+, therefore lowering our pH. Now, if you put both of these in a sample together, or a beaker together, or something like that, so think about the fact that this completely happens. So this is all you got from this guy over here, okay? He has no equilibrium. He completely goes to completion. Very, very product favored. Okay, now this one is already reactant favored. You do have a little bit of dissociation going on. But when you put this in there, it's got the H+ in common. So it's like common ion. So you're just adding H+, H+, H+ over here. So it's going to shift this way to make more of the bound acid and less of the H+. So at the end of the day, if you've got a strong acid and a weak acid, you're definitely only going to focus on the strong acid. If you have two strong acids, that's a little bit different story, which we will talk about in just a second, because they're both going to completely dissociate. So you need to account for the amount of H+ in both of those if you have a strong and a strong. And then if you have a weak and a weak, we're going to approach that very similarly to a polyprotic. Okay, so example. So we want to find the pH of a solution if we have 50 mils of this HCl and 50 mils of acetic acid. Okay, so one thing that you have to consider here is that we're only worried about the HCl's H+, right? So we know that HCl is going to give us this many H+, right? And that's in the 50 mils of solution. Now, the problem is when you put these two together, what you have done is you have changed the volume and therefore the concentration of your H+. So you've got to find out how many moles you have from that HCl. HCl is giving us all our H+. So I need to use my molarity equals moles over liters calculation to determine the number of moles that HCl is giving us for H+. Okay, so I got, and then we got 50 mils, so that's 0.05 liters. So that means we end up with 0.005 moles of H+. All right, now we need to divide it by our new total volume. So we got 50 plus 50, that's 100 milliliters. Convert it to liters, it would be 0.1 liters. So 0.005 divided by 0.1 is going to give us a concentration of 0.05. Okay, so this is our H+ concentration. Now to get to pH, we're just going to simply negative log that. So negative logging it. And we get a pH value of 1.3. Okay? All right, so this is definitely what you want to do. You've got to determine which of your acids is giving you your hydrogen. It's always going to be the strongest acid. We have a strong HCl, a weak acetic acid here. And then you've got to get your moles of H+, out of that HCl, and then divide it by your new volume because you added some more solution to it, and then negative log it. Let's look at this second example. So in the second example, we've got HCl and HNO3. Okay, so hopefully you're thinking, oh, that's definitely a strong acid, and that's a strong acid. So that means that we're going to have to determine the number of moles for both of them. this time. So we've got molarity equals moles over liters. So again, I got 0.1 equals my moles over 0.05 liters, which is 50 milliliters. So I get 0.005 moles. Okay, so that's pretty much my HCl, right? We also know that HNO3 is a strong one, and because it has the exact same values, it makes my life very simple this time, because it just means that I also have 0.005 moles of H plus in the HNO3 as well. So this is how many moles of H plus I have total. So I've got 0.01 moles of H plus total divided by my total volume. So my volume is 50 plus 50, so that's 100 milliliters. So 0.1 of a liter. So divide this, and we get the answer of, let's see, 0.1. Okay, so, and then I'm going to do, this is my H plus, and then I'm going to plug that into pH equals negative log of 0.1. So my pH is equal to 1. Okay, so you're probably thinking, well, like, why did you do all that? Because, you know, this one is, you know, they're both giving you the same H plus concentration. Okay, that's completely true. And, but the thing you have to understand here is these had the same concentration and they had the same volume. So that wasn't going to change anything. However, if I had a different concentration or a different volume, if everything didn't match completely, then this is definitely the way to go by finding the moles from each of the acids and determining, you know, adding them together essentially. Okay, so that's definitely the way you want to go to make sure that you don't get confused. All right, in this final example, you see that we have this phenol and this acetic acid. We're given the Ka values for both of them. So we've got two weak acids here. So when you have two weak acids, you basically want to look at the acid that has the stronger. The stronger one is the one that's going to provide the majority of the H pluses for the solution. So definitely our larger Ka value is the acetic. So I just need to focus on that one as far as giving me how many, for looking at our H plus concentration to get our pH. However, because we added the additional 50 mils of, wrong 50 mil, because we added the additional 50 mils of this phenol, that is going to have a change in the concentration of the original acetic in solution. Okay, so we need to do the same thing that we've been doing. We need to say, okay, let me find out how many moles of acetic acid I'm going to have. So I've got a 0.1 concentration and 50 milliliters, which is 0.05 liters. So I've got 0.005 moles of the acetic acid. And then we know that it is in a new volume of 100 milliliters, which is 0.1 of a liter. And so that gives me a new concentration for my acetic of 0.05 molar. Okay, so because this is a weak problem, no matter which way you look at it, we're just going with the higher Ka. We still definitely want to do an ice table and plug everything in. So I'm going to write my dissociation equation real quick. And then we're going to calculate our H pluses, and then we'll be done. All right, so here is my initial amounts for my acetic. We're going to lose this. And then these we don't have any of, so we're going to be adding to these plus x. So you end up with x squared over the 0.05. Remember, we can scratch off the minus x part because Ka is a small number. So 1.8 times 10 to the negative fifth. All right, so we're going to cross multiply that up, take the square root. So we find that our x value is 9.5 times 10 to the negative fourth. Now that's my H plus concentration, essentially. Okay, so now I'm going to pH equals negative log of that number. So this whole number is going to go over here. and I get a pH of 3.02. There you go.